Section 7.3, triangle similarity, angle similarity, side, and side angle side. So this is a little like what we did in chapter 4 with triangle congruency and showing certain requirements that have to be met in order to say two shapes are congruent. Now we're looking at certain requirements to say two shapes are similar. So what we saw in section 2, similar shapes or similar polygons have a 1-to-1 ratio with their angles, so the angles are congruent, and then there's a proportion with their size. So every side in one triangle or polygon to every side in another triangle or polygon has the same ratio. So equal ratios making a proportion, and we want to show the proportion between sides or show the 1-to-1 ratio or congruency with the angles. So we'll start with angle similarity. Now if you remember from chapter 4, I believe, if we have two pairs of angles that are congruent in two triangles, then the third angles theorem means the third pair of angles are also congruent. So if every pair of angles has a 1-to-1 ratio, so all the angles in one are congruent to all the angles in another, we can say the triangles are similar. But again, we're trying to go with what's the bare minimum information. So because we could always use third angles theorem, we only need to know two angles that are congruent between the two triangles. Because third angles theorem can automatically get us the third. So all we really need are two. So not really writing a proof for this, but just explaining why these two triangles would be similar. So we have those right angle markers, those boxes. So we know angle A is congruent to angle D. And that is because of the right angles congruence theorem. You know, any two right angles are congruent. Now you could say definition, they measure 90, substitution, they measure each other, definition of congruent angles, they're congruent. You could do all that. Or you could remember the shortcut, the theorem, the right angles congruence theorem. All right angles are automatically congruent to each other. We also know, because we have opposite angles on opposite sides of an intersection, so vertical angles, angle BCA is congruent to angle BCA, so not toward the right angle, then towards it. So in this triangle, use the same order. So not toward the right angle, then toward it. So ECD. So angle BCA congruent to angle ECD by some good old that, vertical angle theorem. So if we have two congruent angles, we can say the triangles are similar. So therefore, 3 dots, kind of a shorthand for therefore, triangle ABC is similar. So we only use the tilde, or the, as I call it, the squiggle. So similar, it's not congruent, it's not equal, it's only similar. So not the whole congruency symbol, just a part of it. Triangle ABC, similar to triangle ABC, right angle up. So DEC We can say that by angle similarity. So not writing a full-blown proof, but just showing how we could logically make the argument that these two are similar to each other. We have two other types of triangle similarity. So you kind of recognize them from triangle congruency. So we use the tilde or the squiggle to say they're similar. So we'll use SSS, so side, 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 and then just add the tilde afterwards. Side angle side or SAS, so SAS, and then the tilde afterwards to kind of distinguish between the congruency and the similarity. So looking at this diagram, could you figure out why those two triangles are similar? What reason could you use? And then you want to find RT, that length. Once you have the similarity and the proportion between the ratio between the two triangles. And then once you find that, check your answer with my completed notes online.